Welcome to qnawire.
Welcome to a new spring problem. So this time you have what we call a spring gun. So this is our spring gun right here, and inside of it there is a compressed spring. This distance of compression, well, we'll extend it a little bit. This distance of compression is 6 centimeters. If you change that to we can call that, instead of just calling it 6 centimeters, we can call that distance x if you want to. So x happens to be 6 centimeters. We change that to meters. SI is standard units. So 1 meter per 100 centimeters. And that becomes 0.06 meters. So what's happening in this problem is that you have a ball inside of this spring gun barrel. The spring constant happens to be K equals to 400 Newton per meter, and the spring has a negligible mass. So this spring has negligible mass, and that helps us in the problem. So it doesn't complicate the problem. The mass of the ball happens to be 0.0300 kilograms, and it's a horizontal barrel, so the spring is going to be released. And when it's released, what happens is it pushes the ball up until the edge of the barrel. So if you look at this, would be like a before and after scenario. This is after. This is where the spring starts. This is the point of release. So it's gonna kind of like stretch all the way up until there. So you still have the ball at the end. So it's interesting then that when it's released and it takes out the ball, the barrel itself is 6 centimeters long. Okay, the barrel is 6 centimeters long. So I think we should kind of like indicate that this barrel, this distance right here, happens to be 6 centimeters, and then this is like outside. Okay, this is outside right here. So this is all outside, and there's a spring there. There's a barrel. Maybe I need to I need to open this because the ball is going outside. So we want to model the diagram to show this is open because it's allowing the ball to go outside. So pretty much what's happening in this problem is that you have a spring that's pushing a ball outside. The spring has a spring constant of 400 Newton per meter. And in part A of the problem, we want to find out the speed with which the ball leaves the barrel. So what's this velocity here? We're going to use the law of conservation of energy, which says energy before equals to energy after. Energy before equals to energy after. The energy before is stored as elastic potential energy, and that happens to be 1/2 kx squared. The energy after is stored in terms of the kinetic energy of this ball right here. So this ball develops some type of kinetic energy because it's moving. And we want to solve for this velocity. So you can see we divide both sides by 1/2. We divide both sides by 1/2 m to make our life easier. This is just algebra. 1/2 m here, 1/2 m here. You can see the 1/2s are going to cancel out, and the m's are going to cancel out. So v squared happens to be kx squared over m. So the velocity with which the ball leaves the barrel is square root of kx squared over m plug in the numbers. K is our spring constant right here. It happens to be 400 Newton a meter, and then the displacement or distance that this ball moves before it leaves outside or before it leaves the spring is 0.06 meters. So we plug in that. Always a good habit to keep track of the units, and then divide by the mass of the ball. And the mass of the ball, as you can recall, is right here. It happens to be 0.03 kilograms. So we keep track of all the units again. This is a square root. Plug in the numbers. You notice the final velocity is the same as 6.9 meters per second. So, that's the velocity that the ball has when it's leaving the barrel. So let me just cross check again, 0.06, and then divide by 0.03, and that gives us 400. Gotta do that again. Oh yes, so square root of 400 times this one is gonna be squared though. This one is squared, so we don't forget that. So 0.06 squared divided by 0.03. Better try it again. The second shift, 400 times 0.06 times 0.06. Not times, but divide by 0.03. Close the bracket. We get 6.9, or we can say 6.93. So, just to be a little bit more precise, we'll call this 6.93. So 6.93, that's the velocity the ball leaves the barrel. The second part of the problem is that we want to get the speed of the ball if there's a constant resisting force inside the barrel. So this is part B. There's a constant force inside the barrel. So once again, you got that, you got the barrel, and then you have the spring. This is the initial position of the ball. It pushes, the spring pushes the ball all the way up, but there's a resistance force acting in the opposite direction. So there's a force that's resisting in the opposite direction. Because it's a resistant force, I'm going to call it FR. Okay, I'm going to call it FR. So from the spring itself has elastic potential energy, which is 1/2 kx squared. This force is working against that, so work done by the resistance force is Fr times the distance that the ball has to move. And so if you put those two energies together, you get 1/2 kx squared minus Fr times x. This one right here, this is the energy that the spring exerts an energy on the ball equivalent to 1/2 kx squared, and then the force exerts an opposite energy on the ball, which is equal to Frx. So this is energy due to the spring, and this is energy due to the force, and that should equal the kinetic energy of the ball itself. So 1/2 mv squared, and then we can make our life easier by multiplying everything by 2. That way you're going to cancel this 1/2 and that 1/2. So we end up having mv squared equals to kx squared minus fr times x. We divide both sides by the mass, which is m. And then at some point we need to we end up having v squared equals to kx squared minus fr times x over m. And the velocity becomes the square root of that, which is kx squared minus fr times x over m. You could pull out the x, so you have square root of x k minus fr all over m. And then we need to plug in the numbers, so I'm going to continue that right here. X, if you go back, happens to be 0.06. So this is 0.06 meters. Remember, it's x. This would be kx right here. Don't forget the kx. And then we have kx. K happens to be 400 Newton meters. Times x, which is 0.06 meters, minus the force. If you go back, you see that there's a resisting force that's stopping the ball from going outside, and we need to include that resisting force, which happens to be remember, there's a 2 here, so let's not forget that. There's a 2 right there, there's a 2 right there, there's a 2 right there, there's a 2 right there. So there's a resisting force, so minus 2 times the resisting force is 6 newtons. If you can recall this force right here, it's 6 newtons. So 2 times 6 newtons, and then times, so in that case, we have to divide by the mass, which happens to be 0.03. Okay, 0.03 kilograms. When you solve that, you get that the velocity, the speed, goes down to 4.9 meters per second. So once again, what's happening here is that at the beginning, we didn't have any resisting force. There was just a spring pushing the ball outside. So we used conservation of energy. Energy before equals to energy after. The before energy was 1/2 kx squared. That's from the spring. The after energy was the kinetic energy that the ball gains. Remember, all the elastic potential energy from the spring is transformed to the kinetic energy of the ball. Allows us to solve for v. It's a good habit to keep the variables up until the end, and that's what's happening right there. Don't forget this square sign. Easy to forget small things like that, and then you get 6.93. In the other part of the problem, now we have a force that's resisting the motion. So in terms of conservation of energy, this is energy before, equals to energy after, law of conservation of energy. The before energy is reduced by this frictional force, not frictional force, but by a resisting force, which I call Fr. So Fr times x, and that's subtracted from the elastic potential energy, and you make that equal to the energy after, which is the kinetic energy that the ball gains. You solve for v squared, and then keep the variables up until the end. It's a good habit. At this point, you're seeing I'm pulling out the x just for purposes of algebra, and then I'm left with kx inside, and then minus 2 fr over m. Solve that, you get 4.9 meters per second. The next part of the problem, we want to know, what's going to happen in a different case. So we still have that. We have the spring. We're assuming, so I've just magnified it. This is 0.06 meters. And then there are certain assumptions that we're making that we want to know what's the point where the ball has the greatest speed. So I'm going to call that x x greatest. That's the point where the ball has the greatest speed. The spring provides a force, which is F equals to K times x greatest. So this is the same as x greatest being equal to F, which is spring force, over the K, which is a spring constant. And so we have 6 newtons or 400 newton per meter. That gives us 0.02 meters. And what that means is that the distance all the way up until the greatest force, this distance right here is 0.02. And so that's the distance moved by the ball. So we have to backtrack a little bit. This one right here, this one right here, this one right here. So the x greatest, okay, x greatest is the same as that whole the distance moved by the ball is given by 6 newtons over 400, and that's going to give us what, 6 newtons over 400. So let's see, 6 divided by 400, that's 0.015. So this is 0.015 meters. When you round it off, you get 0.02 meters. So the actual distance moved by the ball, which we call delta x, becomes 0.06. That's the total distance from right here to right there, minus 0.04, minus 0.02, sorry, and that gives us 0.04 meters. So that's the distance moved by the ball. The other part of the problem, the last part of the problem, we have to use the total work involved. And the purpose of using the total work is we want to find out what's the greatest speed, the greatest speed. You know what? I should just call this, instead of x great, I'm calling it x greatest because this is the point where we have the greatest speed. Okay, that's the point where we have the greatest speed. So we want to compute that. We're still using the law, the law of total work, if you want to call it that. So that's the kinetic energy plus any other external work equals to elastic potential energy, or change in elastic potential energy. So this one we can call it change in elastic potential energy. I'm going to erase that right here, is equal to change in elastic potential energy. So change in kinetic energy up until the maximum velocity, we have mv squared greatest equals to, not equals to, but plus, so we're using the total work, plus the force it's going to take, the resisting force up until the end, minus up until the greatest position, which is So x greatest happens to be, I'm calling it 0.02. Okay, x greatest is 0.02, so minus x greatest, that's a special location, equals to 1/2 k x squared minus x greatest squared. So that's just the change in elastic potential energy that happens. So, this is the change in this one right here is the change in work done by the resistance force, change in work done by the resistance force. And this is change in elastic potential energy. So we multiply everything by 2 to make our life easier. So this is mv greatest squared plus 2f x minus x greatest equals to k x squared minus x squared greatest. So it can be a long problem. Our goal is to get this one, v greatest. So we're going to have, on the next page, we have mv greatest squared equals to, remove everything to the other side. We get k x minus x greatest squared, or both of these are squared, minus 2f x, we're taking that number right there, x minus x greatest. Again, our goal is still to solve for v squared greatest, so you can see that v squared greatest is k x squared minus x squared greatest minus 2f x minus x greatest all over m. So this m, we divided m on both sides, as you can see. So now we're ready to find the final velocity. So v greatest, it's just going to be the square root of all of these numbers. So we plug in those numbers and get 400 Newton per meter times x, which is 0.06 meters squared, minus, we have a bracket here, minus x greatest, which is 0.02 meters squared. Okay, and then minus 2. The force is 6 newtons. And then we're going to get a 0.06 minus 0.02. That's the change in displacement all over the mass, which is 0.030 kilograms. And so our final answer happens to be 5.2 meters per second. So that's the largest speed. That's the greatest speed, the v greatest. So once again, a long problem involving a spring and a ball. The spring is pushing the ball outside the barrel. So we want to find the velocity when the ball gets to the mouth of the barrel, which happens to be 6 centimeters. And that's what we got right here, this velocity. Using the law of conservation of energy, before is the same as after. The energy, on one side we have elastic potential energy, on the other side we have kinetic energy. In the second part we have an external force coming in, so we have to account for that. The external force is taking away from the kinetic energy, and this is what's happening. This is the kinetic energy and this is the external force, so it's reducing the kinetic energy, and it's reducing it because it's reducing the elastic potential. So When we make that equal to the kinetic energy, we solve for V by reorganizing the problem, keeping our variables up until the end. The next part of the problem, we have to find the point at which the greatest speed happens. We use Hooke's law, F equals to kx, and solve for x greatest, which gives us 0.02 meters. We can get the change in displacement by subtracting it from the largest length. And then the final part of the problem, we have to use the total work formula, where we say, the total work done in the whole system is a constant, stays the same. So, we have kinetic energy at the greatest location is the same as the change in work done due to the resisting force at the greatest location, which is equal to elastic potential energy. We plug in the numbers, we do a lot of manipulations, and you can see at this point we solve for the V greatest, which happens to be 5.2 meters per second. So thank you very much for watching the video. Have a wonderful day. If you have any questions, just send them my way, and I'll be glad to respond to your questions. Okay, thanks. Bye.